Hello everybody, this is Avantik here. Today we'll be discussing about anomaly detection. The agenda for today's discussion would be understanding what are outliers and the different techniques which we will be using for identifying outliers. The first of them is statistical based methods. We'll discuss z-score based methods and IRQ based methods over there. We'll use Gaussian mixture models to identify outliers. Then we have covariance methods like elliptical envelope. We'll make use of that to identify outliers. Random forest methods are there, like isolation forests. We'll be exploring that for this. Then you have nearest neighbor based method, which is known as local outlier factor. We'll be using that to identify outliers. Then a clustering based method like DB scan. Let's see how we make use of all of these in identifying anomaly data. Let's first understand what are outliers. Outliers. You have a data which have a general trend. That means which have a distribution to which the data fits in. And there are some piece of data which does not fit in the general trend of the data or say general distribution of the data. These are known as outliers. Data belonging to the general trend are known as inliners. Learning models are usually impacted by the presence of outliers. Long before, when we were discussing linear models, we mentioned how linear regression is impacted by presence of outliers. So we need to treat the data properly before we can subject them to our models. Okay, anomaly detection is another use of outlier, the data which shows unusual behavior, right? Those are known as anomaly, and we want to detect them so that we can identify frauds with them, right? We can identify unexpected behavior with them. Okay, we'll now understand different methods to deal with outliers, and once we detect them, we can either delete the outlier data or we can actually mark them so that the learning model are aware that these are some special kind of data. Let's start with statistical based methods. Statistical based method for univariate data, and they will use methods like z-square and IRQ for identifying outliers. So let's generate some normal distribution of data, and we'll use for standard deviation method. So if the data is normally distributed, 97% of the data will fall under the major section of it. And what we are interested in finding the data which is towards the, if you talk about normal distribution, right, the majority of the data will fall under this bell curve, and they're very minimalistic data which will be in the edges, and what we are interested in finding them. Okay, so let's now first generate some normal distribution data. As we can see here, that's what we are doing, adding some outliers. Okay, so we are adding last 5 data with these values. SciPy provides you z-score function which gives you z-score. Okay, so what you are doing here is we are trying to get data which has z-score greater than 3, and this is what we fetch, right? So z-score greater than 3 is a good indicator that this is at the data is at more than 3 times standard deviation from the mean. Okay, that's what it means. The data is at the 3 times of standard deviation from the mean. So we consider them outliers. Okay, so this is one method that can be used. In case your data is not normally distributed, you can use interquartile IQR method. Okay, and how we do that? So just to recap for folks who are new to this, your major the data which contains outliers, the 25% of and 75% of the data will be very much stabilized, right? So we want to use them as a benchmark and identify our outliers. So IRQ is the difference between them, the 25% of the data and 75% of the data. You can directly calculate them as IRQ. So in this case also we are generating the data, adding some outliers over there. Then you have IRQ. Remember, IRQ will be the difference between 25th percentile of the data and 75th percentile of the data. Okay, and now we want to have the lower threshold below which we will consider everything as outliers, and above an upper threshold above which we'll be considering them as outlier. So this is our 25 percentile of the data. So, and we can see here IRQ into 1.5. So just 1.5 times value of IRQ below your 25 percentile of the data. Below this, whatever data we have, that will be outlier. Remember, these techniques are for univariate data. Okay, the same thing is for this guy. So based on this, what we are calculating is these are our outlier data below the lower threshold. These are the outlier data above than the upper threshold. Right? So these are the univariate method. That means you are considering only one column at a time. Okay, let's proceed with Gaussian mixture model, which will be, which can be used for different reasons. Let's see them. Gaussian mixture model. Gaussian mixture model. Okay, so normal distribution talks about you have one peak in the data. Now assume you have multiple peaks in the data. Okay, that is where your Gaussian mixture model comes into picture. Okay, so rather than predicting one pattern, you want to have multiple multi-model in the data. Rather than having one Gaussian distribution, you say that your data consists of multiple the subpopulation. There are multiple subpopulations which shows normal distribution. Okay, rather than the entire population showing normal distribution, you can say you want to find fit for multiple subpopulation showing normal distribution. Okay, so Gaussian mixture model allows you to fit such multi-models. Now in situations like this, you have a parameter and components which tell you how many such peaks are you expecting, right? So it is highly parameterized. You have to configure number of peaks that you are expecting. Also you have covariance type, okay, which is basically how the distribution would be. For example, if you configure full, the predicted cluster can be eclipsed in any direction. If you're configuring spherical, if you consider spherical, it can be the clusters will be spherical like k-means. If you configure diag, the eclipse will be along the axis. Okay, let's see how Gaussian mixture model can be used to predict outliers. So the first thing is generating the data. As we can see, we are generating the data, and we are adding some outliers, as you can see here. Okay, and we are plotting it. You can see this is the distribution of data. So and this is some outliers that we have. Now we'll use Gaussian mixture model, and we want to use number of peaks as to, of course, these are things of hyperparameter tuning, but we'll use 2 peaks here. So we need to configure number of components as 3, since we have 2 peaks, and one will be the distribution for the outliers. So we have to mark it 3. Okay. So of course, these value will come after you, hyperparameter tuning. You need to see which one is giving you the outliers, and based on that, you will choose these values. Okay. So once you have configured this 3, you are predicting the model, and after that, when you call predict, right, it's giving you the cluster to which it belongs, and once I plot it, you can see this is purple is one distribution, yellow is one distribution, and you can see some blue here. This is another distribution, and these are the outliers, right? Okay, so this is how we can use Gaussian mixture model to identify outliers. We'll check out our next guy, which is elliptical envelope, and see how using that we can identify outliers. Elliptical envelope. Now we understand that elliptical envelope, the assumption is the that regular data shows known distribution, like Gaussian, for example. Inliner location and variance can be calculated using Mahalanobis distances. Okay, so which is better than Euclidean distance, right? And much more stable in terms of if outliers are present over there. So what we do over here, we want to predict the envelope, elliptical envelope, which more or less represents the data. For example, we have a data which looks like this. Okay, and if you use elliptical envelope, it will try to have an envelope. This will be the output here, right? It's try to predict an eclipse in the data. Okay, and of course, this will be controlled by contamination. How much data, how much percentage of the data you're considering as outliers. If you increase the value of contamination, your yellow its eclipse size keeps on decreasing. That means that is the level of contamination you are configuring. That means this means 10% of the data are outliers, right? So based on that value, so elliptical envelope tries to predict an n-dimensional envelope which will consist of the core data. Okay, so data which can be outliers will be little far from this envelope, right? So you can use predict, and you can see in this notebook that it is predicting the outliers here, the yellow being the inliers, the purple ones is the outlier. You keep changing the value of contamination, you will see more and more outliers if you increase this. So this is the percentage. Okay, so after this we'll understand isolation forest. Isolation forest is a random forest based technique to identify outliers, and very useful in detecting outliers in high dimensional data sets. Given a data, it randomly tries to split the data based on a feature. Of course, it chooses feature randomly, tries to split the data. So the important thing to understand here is anomalies can be reached with shorter paths, right? So okay, so what we'll have with isolation forest is lot of trees, and from those trees, whichever data we can reach with lesser path, we can consider them as outliers. Okay, so again we have the same data. Okay, so we are generating data here, and we are using isolation forest. The hyperparameters in this case are behavior, new, and contamination auto. This is required as per the current release. So okay, if you don't give it, it will throw warning. Okay, otherwise you'll use the same stuff. So it is mandatory to configure them. You can refer documentation if you need further details on this, but these are defaults. And you're using predict, and you can see here it automatically predicts that these are the inliners and the purple one are the outliers, right? This is very much suited for data which shows higher dimension. The next method that we'll see is nearest neighbor based method, that is local outlier factor. A local outlier factor. So this is the nearest neighbor based method to identify outliers, suited for moderately high dimension data set. And the important part here, it not only considers how outlier one particular data is, but how outlier one particular data is with respect to the all other data. Okay, so it uses nearest neighbor as a core concept. Let's understand how this LOF is calculated. If LOF is local outlier factor, so this is based on nearest neighbor, suited for moderately high dimensional data set. LOF computes a score reflecting the degree of abnormality of data. So LOF, this term local outlier factor, this is a value, okay, scalar value. This tells you how outlier a data is. Okay, as I'll once we can calculate that, I'm plotting that in terms of size of this data. So you can see the data which is far from the actual cluster, right, is showing higher values. That's why the size is bigger. Okay, so this local outlier factor is the one that we have to calculate for each point. So let's see how to do that. So the core thing in nearest neighbor is it has a local density. Okay, so all the points of nearest neighbor cluster, right, has a local density value. All for all that a point data has to do is calculate the average local density of the cluster, then and calculates its own local density, and the ratio of it will be actually LOF all that of that point. So if the LOF of that point is very less, we can say that that point or data is outlier. Okay, and the important point to consider in local outlier factor is it not only consider how outlier one particular data is, it considers how outlier one particular data is with respect to all other data. So let's see how to do that in code. You have sklearn.neighbors. You're importing local outlier factor. You're configuring n neighbors equal to 25. That means you're considering 25 neighbors, and the contamination factor is 1. Okay, that means 10%. So let's see here. We are fitting the model, and once you have fit predicted, the model predicted actually returns if it's outlier or not, but we are interested in how outlier is the data. So it's a very important factor. So we can do that with LOF.negative outlier factor. It tells you how outlier is the data. So np.abs, because all these values will be negative, you want to show them in size. That's why we're multiplying 10 here, and that's what you see here, that data which is far from the core of the data is considered to be outlier, and data which is very far will have higher value of this, right? Remember, this negative outlier factor will be negative. That's the reason that smaller or greater comes into picture. Okay. After this, we'll understand DB scan, which is a clustering based method to identify outliers. Outlier detection using DB scan. This is a clustering method. We have seen that in clustering module as well, but to make it use of making use of DB scan for outlier detection, let's see that now. Okay, all that it does, this clustering method, given a point, it tries to find nearest dense cluster and goes to that. So even after a process like this, if there are some points which does not get assigned to any cluster, you can conclude them as outliers. Okay, so let's see them. We have this DB scan, and we are configuring this value as 0.3. So higher the value, this is the range to which, like, we can see how to impact this. DB scan current code, we see this. If we try to decrease the value, right, we can see this is the distance to which it allows somebody to be part of the cluster. So if you increase it, you can see here, it allows more data to be part of the cluster, right? And you can see these points, or we will repeat this. It's taking the older value. Yeah. Let's start with DB scan. DB scan is another clustering method using which we can identify outliers. The philosophy or the intuition in which DB scan works is, given a point, it will try to find the nearest dense cluster and it will try to be part of it if it is in the range of 0.3. Okay, so this controls to what extent, to what distance a point can be part of a cluster. Okay, if you increase this, further and further points can be part of a cluster. If you decrease this, your cluster size will shrink. Only the closer ones will be part of the cluster. Okay, so we are configuring them here. You have DB scan, you are configuring them with EPS value 0.3. If you decrease this, you allow a very less gap between the cluster and the point. You can see here. Okay, if you increase this, right, you allow a little far data to be part of the cluster, and we are plotting this over here. DB scan labels give you the class. So you can see there are two major classes, and these values will be actually -1. Okay, the outliers will be represented as -1. We can see them as DB scan dot labels, right? We can see some values as -1. So -1 will be outliers over here. Okay, that's all from anomaly detection. Hope you guys enjoyed it. Thank you.